Now that we have obtained the MED for the major and the minor axis of the column, which is calculated from these equations based on the stress diagram for the braced slender column. Since the column is subjected to moment in both axes, we might not be able to take straight the calculated MED without considering the effects due to the biaxial bending. The biaxial bending might take effect, it might not also. This is very much subjected to the geometrical properties of the column. At the moment, we don't know whether the biaxial bendings will give the effects to the moment design. Therefore, we will need to go through a check to see if we can ignore the effects of the biaxial bending. With the calculated MED, we put this on hold first. In the case that the biaxial bendings can be ignored, then this value shall be used in the design of the reinforcement. You will design the reinforcement for the major axis, and then you do the design for the minor axis, and then work out a common layout of the reinforcement bar, which providing sufficient amount of reinforcement in both major and the minor axis. This is when the biaxial bending effects can be ignored. In the case that biaxial bending effects cannot be ignored, that means the calculated MED here will have to add up with the biaxial bending effects due to the other axis. Ultimately, the MED here will be larger than what you have calculated based on the stress diagram here. Having this understood, let us deal with the next question. How do you know whether biaxial bending can be ignored? There are 4 items here that we need to check. Among the 4 items here, these 2 must be fulfilled. And then either of these 2 will have to be fulfilled. In the case that any of these 2 is not fulfilled, that means you have to check for the biaxial bending. Or if none of these 2 requirements is fulfilled, then you have to deal with the biaxial bending. These 4 items that you need to check are purely geometrical properties, where it is in the functions of the effective ratio of the major and the minor axis, as well as the eccentricity versus the dimensions of the columns. Having this understood, we will work out the numbers. First, we deal with the effective ratios. The effective ratios are given in the question here. You are actually comparing the slenderness ratio in the major axis against the minor axis. Take the slenderness ratio of the major axis divided by the minor axis, and then take the slenderness ratio of the minor axis divided by the major axis. The calculated values are 0.55 and 1.81. The requirements are those ratios shall not be more than 2.0. The calculated value 0.55 and 1.81 are all less than 2.0. That means these 2 requirements are fulfilled. Next, you need to check these 2 items. To do this, you need to get the equivalent eccentricity as well as the equivalent dimensions of the column. Let us deal with the equivalent dimensions of the column first, since it is easier. We have the equations for the equivalent section. These 2 equations are used only when the column is not in the square or rectangular shapes. In this case, our column is rectangular in shape. That means we do not need to work out the equivalent section. Instead, we can straight away take the dimensions of the column as the equivalent section. As a result, the H equivalent, it will be 300 mm, which is the bigger dimensions of the column, whereas the B equivalent, it will be 150, as it is the minor axis. And then next, we deal with the equivalent eccentricity. This is calculated on the basis of the moment acting onto the column divided by the azimuths. You may refer to the diagram here to determine the EY and the EZ. EY, it will be calculated on basis of the y-axis, whereas EZ, it will be calculated on the basis of the z-axis. Assuming now your azimut and ED is not acting exactly onto the centroid of the section. This is due to the existence of the moment acting onto the column, which will give you a resultant NED slightly off from the centroid of the column. For you to get the EZ, we are looking at the moment here, which is the MEDY. That's why the equations for the EZ, it will be equals to MEDY divided by NED. Now, if you want to calculate the EY, that means this will refer to the moment in the Z axis. That's why you have MEDZ divided by NED for you to get the EY. Now, where do you get the MED? Remember, previously we have calculated the MED in the major and in the minor axis based on the equations for the slender brace column. That means, for you to calculate the EZ, you use MEDY divided by the azimuths, which is 147.36 kilonewton. That gives you 176.4 mm. To calculate the EY, you need MEDZ 31.6 kilonewton meter divided by NED, which is 147.36. That gives you 214.4 mm. Now you're going to calculate those ratios. Get EZ divided by BEQ, the whole thing divided by EY divided by HEQ. You obtain 1.65. And then you do the same for another ratio. EY divided by HEQ, the whole thing divided by EZ divided by BEQ. You get 0.61. The requirements are these two ratios here will have to be less or equals to 0.2. However, the calculated results are 1.65 and 0.16. These values are larger than 0.2. This leads to a situation that these two items are fulfilled, but none of these two are fulfilled. Not being able to meet those conditions, that means you cannot ignore the biaxial bending. Now you know that the effects of the biaxial bending will have to be taken into considerations. At this stage, you know that later the design MED will have to be greater than what was calculated from the equations for the MED. Because these equations consider the MED on the individual side of the major and the minor axis. The MED here has not incorporated the biaxial bending effect due to the other axis. Now we know that biaxial bending will bring effects to the moment design. Our next step it will be to determine which side will be critical. We need to first know which side is more critical in order for us to work out the MED that you may use to determine DAS from the design chart. The criteria to determine the side which is critical lies with the ratio between the moment versus the effective depth of that particular axis. H' and B' represent the effective depth as indicated in the diagram here. This is calculated by having the dimensions of the column minus the concrete cover, which is 35, minus the shielding, which is 6 mm, and minus half of the bar size, which was 20 mm divided by 2. If we do the same for the other axis, the larger dimension will be the H' and the smaller dimension it will be the B'. Now that you have your H' and the B', we will use the MED that we have calculated previously to be divided by the H' and the B'. For the major axis, we take the major axis MED divided by the effective depth of the major axis. That gives you 126.9 kN. As for the minor axis, we take the MED from the minor axis divided by the B'. That gives you 264.5 kN. Compare the two values here. The minor axis is larger than the major axis. This gives you an idea. The minor axis it will be more critical than the major axis. Therefore, for you to determine the MED that is used in the design chart to determine the DAS, the minor axis MED shall govern. Therefore, you will take the MED in the minor axis plus the effect due to the major axis. That will give you a new MED known as M'EDY. Having this understood, we have the MEDY, which is 26 kN in the minor axis. We need to get the beta. Beta is given by this equation in the functions of NED divided by BHFCK. NED is given 147.36 kN divided by BH 150 times 300 and also FCK 30. You find your beta equals to 0.91. Make sure the betas fall in between 0.3 to 1.0. 0.891 is between 0.3 to 1.0. That means you can take beta equals to 0.891. And then you go with the equations. Since you are dealing with the minor axis, then you are talking about the ratio in terms of the minor axis divided by the major axis. And then this whole thing here is to be multiplied with the MED in the major axis, which is 31.6 kN. Substitute the relevant value into the equation. You get the M' MED Y equals to 37.4 kN. Next, you will use this to determine the amount of reinforcement bar for the column. This is done by applying this MEDY into the column design chart. Before that, you will need to determine which chart to be used, since there are quite a number of charts here. To do so, you will need to first calculate the D2 per H ratio of the column. This is D2. which is calculated from the concrete cover plus the shielding plus half of the bar size. The concrete cover is 35 mm, shielding 6 mm, and the bar size 20 mm. This gives you D2 equals to 51 mm. Next, you need to calculate the D2 per H. First, this MED is in the minor axis. Therefore, your D2 per H it shall also be on the basis of the minor axis. That means the H here now, it will be equals to 150. Dividing 51 by 150, you get D2 per H ratio of 0.34. Among the design chart, you have no D2 per H ratio more than 0.25. Therefore, we shall use the D2 per H ratio equals to 0.25. Next, it will be the applications of the chart. Refers to the y-axis. You need to generate a number for n per BH FCK. The n is the absolute, which is given as 147.36 kN, BH 150 times 300, and FCK is equals to 30. Therefore, you get 0.109. As for the x-axis, you need to generate a number for m per BH square FCK. This m here, it will be the one that you have calculated previously, taken into the considerations of the biaxial bending effects due to the major axis. Now your m is 37.4 kN divided by BH square FCK. Since you are designing the minor axis, that means you are concerning with this moment rotation, leading to you this will be the B and this will be the H. Therefore, your B it will be 300, H it will be 150. Square the H times FCK, which is equals to 30. Then you obtain 0.184. Use those numbers to find the AS FYK per BH FCK. Draw a horizontal line for the y-axis, which is equals to 0.109, and then draw a vertical line at 0.184. The two lines intersect here, which falls in between the curve of 0.6 and 0.7. Estimate the locations. It is somewhere around 0.66. That means AS FYK per BH FCK equals to 0.66. Use these equations to find the AS. That leads to you 0.66 multiply BH FCK 150, 330 and divided by FYK, which is 500. This gives you the AS required 1782 mm square. You will need to provide the amount of reinforcement bar greater than this value. In this case, we provide 6H20, giving you a total of bar area 1885 mm square. Your AS provided now is greater than the AS required. That means it is acceptable. And then you will need to check the provided reinforcement bar in terms of the minimum and the maximum bar area. We check the minimum bar area first. This is the equations for the column. About 10% of the absolute divided by FYK with the partial factor of safety. NED is 147.36. FYK is 500. your AS minimum based on this LED, it will be 34 mm square. This needs to be at least greater than 0.2% of the cross-sectional area of the column. The cross-sectional area of the column is taken as 150 times 300. That gives you AS min 90 mm square. The bigger value of the two is selected. That means your AS min will be equals to 90 mm square. Check the AS min against the AS provided. The provided reinforcement bar area is actually greater than the AS min. Therefore, it passed the AS min. Next, we will check the reinforcement against the maximum rebar area. Use the AS provided divided with the cross-sectional area of the column, which is 150 times 300. It gives you more than 0.4% of the cross-sectional area. This has already exceeded the maximum bar area limit. Also, at the lapping regions, it is more than 8%. That means the maximum bar area has been exceeded. In another word, even though your AS provided is greater than the AS required, but the provided amount of reinforcement bar is too much. This might result in the members to be overly reinforced. As a result of this, brittle failure may occur. Because of this, there is no point for you to proceed with the following calculations, such as calculating for the shear length, as well as checking for the biaxial bending capacity. Having the AS provided exceeding the maximum rebar area, it means that the proposed section is too small. You will need to enlarge the sections and then go through the design calculations again. You may choose to enlarge the H sections or the B section. Normally, we will enlarge the B sections, since based on the calculation here, the minor axis appear to be more critical. Enlarge the H sections will still have the minor axis to be more critical. From the practical point of view, ultimately the amount of reinforcement bar required will still be governed by the minor axis. Normally, designing the reinforcement bar in the minor axis will result in more reinforcement bar required. Therefore, you could consider increase the B sections, probably from 150 to 175 or even to 200. If you have no limits in terms of the column size, you can go for a bigger B. As a result of revising the B here, there will be several areas in the calculation step going to be revised, such as during the computations of the second order moment. The effective net here shall change, leading to you changing of the ratio of 1 per R naught. And then this shall subsequently affect the M2, which may or may not influence the MED, depending on the M02 as well as the other component constituting M2. Also, changing the B of the column, let's say here 150, will change the geometrical property of the column. Then you will have to go through again the biaxial bending check. See if the biaxial bending would influence the MED calculated earlier on. If the answer is yes, then you will need to determine which side it will be more critical. Having the B change might changes the ratios. We will need to go through the proper calculations to determine whether the major axis is more critical or the minor axis is more critical. From there, you will calculate the MED prime. Then you will go through the calculations to determine the amount of reinforcement bar. check the maximum and minimum bar areas. If all pass, then you may proceed with calculating for the shelling, as well as checking for the biaxial bending. Make sure this holding does not exceed 1.0. It is when the proposed reinforcement bar fulfill all the requirements, the column is safe to be used.